So to start off with our curve sketching, we're going to look at things we should notice. By looking at the equation, things hopefully we notice. So there are our basic curves. Straight lines, well, one would hope we've got that under control by now. So most simplest straight line, y equals x. And if you had to think of how to recognize it, oh look, both of the pronumerals to the power of 1. So y equals x. Parabolas, well, that became our quadratic. So now one of the pronumerals is to the power of 2. And in general, of course, we have ax squared plus bx plus c. And we spent a fair bit of time looking at quadratics. And of course, the linear function and the quadratic function are very important, because remember, every polynomial can be factorized down to be a combination of linear and quadratic functions. And I guess that's why we spend so much time looking at those two specific ones. Then of course cubics, power of 3. So we see 1's to the power of 3. Now the basic shape of a cubic depends. Now there's a general one, ax cubed bx squared plus cx plus d. The shape that I guess we're used to seeing, y equals x cubed, it will only have that shape if it's a perfect cube. So you can factorize to be something all cubed. Otherwise, it would be something that has two turning points, so it goes up and down. Then polynomials in general, we spend a bit of time looking at polynomials. Okay, hyperbolas. Yes, our basic one, which we now know is what we call a rectangular hyperbola. So basically you're looking for things like one of the pronumerals is on the bottom of the fraction, or you see the x and the y multiplied together. So that's probably going to be some sort of hyperbolic function. Exponentials. Well, that's when we see a pronumeral in the power, or the exponent. Circles. X squared plus y squared is the radius squared. Hey, both of the pronumerals are now to the power of 2, but also the coefficients are the same. Because if they're not the same, we get an ellipse. But of course with these, whilst they're not the same, they are the same sign. Because if they're different signs, now we have the other hyperbola that we looked at, x squared minus y squared, that sort of thing. Logarithmic functions, very hard to pick these ones. You see the word log, you might have a log function. And of course all our trig functions that we've looked at, sine, cos, tan being the three basic ones, but of course we have the reciprocal ratios as well that we've seen. And now we've also seen inverse trig. So inverse sine, inverse cos, inverse tan. So they're pretty much all the basic shapes that we've looked at. Then we can use ideas about symmetry. So if we recognise it's an odd or an even function. So odd functions, function negative x equals negative function x. We know that one has rotational symmetry. And that also means it will always have an x-intercept of 0 if it is continuous at that point. I mean, the hyperbola there, y equals 1 on x, it is an odd function. It doesn't go through the origin though, because it's not continuous there. But any other odd function which is continuous at 0 will go through the origin. Even function, that's the one that has line symmetry. Function negative x equals function x, so symmetric about the y-axis. We talked a little bit about this when we were looking at inverse functions, but not a lot. Symmetry in the line y equals x. How you recognise it is if you swap the x and the y's and you get exactly the same curve, then it must be symmetric about y equals x. It is its own inverse, if you like. Remember we said inverses were reflected in y equals x? So a curve, if it's its own inverse, then it must be symmetric. So an example of that would be x cubed plus y cubed equals 1. Swap the x and the y's around, you get y cubed plus x cubed is 1. It's the same thing. Y equals 1 on x, the hyperbola. Swap the x and the y's around, you get x equals 1 on y. Well, you could rearrange that back into y equals 1 on x again. And if you look at that hyperbola, the basic one, sure enough, yes, there is symmetry in y equals x. I suppose the circle, but I mean, circle's symmetric everywhere, but if you swap the x and the y's, you get the same thing. This idea of dominance. So if you've got two functions multiplied together, things like that, well, does a term dominate? Now, in a polynomial, the leading term always dominates. And that's why we have that idea when we're drawing polynomials. We just look at the leading term and say, hey, where does it start? Where does it finish? Well, that's another way of saying what's happening out at negative infinity, what's happening out at positive infinity. So the leading term always dominates in a polynomial. So this one, x to the power of 4 plus 3x cubed minus 2x plus 2, would start and finish like x to the power of 4, because it dominates in that one. And basically when we're saying dominate, because we're talking about really large numbers, infinity if you like, when you sub that into the power of 4, it's just so much bigger than x cubed and x. So they're insignificant. Exponentials always tend to dominate because they just increase so rapidly. If you think of the exponential curve, starts off shallow, but then gets very steep very quickly. And that's basically what you're looking for with dominance. Which function would increase the most rapidly? Which one gets bigger quicker? But if you're ever unsure, don't forget the basic idea of substituting numbers in. Now pick a big number, maybe 100, see what it's doing, then 1,000, 10,000, and you'll start to get a feel for whether this function is getting bigger, is it approaching 0 or some other number. Asymptotes. Okay, we know vertical asymptotes, bottom of the fraction can't equal 0. Horizontal and oblique asymptotes, top of the fraction is a constant, then the fraction can't equal 0. Remember, a curve can cut horizontal or oblique asymptotes. It is possible. If the order of the numerator greater than or equal to the denominator, do your polynomial division first, and then that function, when you do the polynomial division, so the, hang on, what is it? Quotient. Divide, yeah. So the quotient would be the asymptote. And our special limit, well, it's technically a 2-unit limit, although you very rarely get asked questions about it in 2. Now you do see the 3-unit a fair bit. That one, limit as x approaches 0 of sine x on x is equal to 1. So when you're doing harder graphs, that might come into play. Okay. So that's just basically looking at functions and getting an idea. But then we've got this whole field of calculus now, which can help us with curve sketching. Okay. So it's a fantastic tool. This topic it used to be called curve sketching without calculus. So the idea was just looking at the equation and coming up with a rough sketch. Doesn't mean we can't use calculus to confirm things if we need to. So you can find your critical points, your stationary points, your inflections and so on. Critical points. Technically, a stationary point is a critical point. Okay. We tend to use the word critical point for the vertical tangent ones, however. So that's when the derivative is undefined. If the derivative is undefined, we get a vertical tangent. Again, if it exists at that point. Stationary points, of course, when the derivative is equal to 0. And then maximum and minimum points. Well, they are stationary points, but then we have to look at the concavity. So if it was greater than 0, concave up, so we got a minimum turning point. Concave down, we got a maximum turning point. Okay. Depending on the function, if it's a difficult function to differentiate, rather than using the second derivative, remember, you just test either side of the first derivative to see what it's doing. Is it increasing and decreasing, that sort of thing. Inflection points. Second derivative is equal to 0, locates possible ones, and the third derivative would not be equal to 0. Again, a lot of times it's just quicker to test either side of the second derivative, depending on the function. If it's a complicated function, yeah, use the second derivative, test either side. If it's just a polynomial, I mean, the third derivative is very quick. Special one. If it is both an inflection point and a stationary point, that is what we call the horizontal point of inflection. And I guess the cubic is the classic one there at the origin. It's stationary. If I was to draw in a tangent, it would be horizontal, but it's an inflection point as well. When's the curve going up? When's the curve going down? We use the first derivative for that. Okay? If the first derivative is greater than 0, that means the slope of the tangent is positive, so the curve must be going up. If it's negative, then the slope of the tangent is negative, so the curve must be going down or decreasing. So we can use the first derivative for those sort of ideas. Implicit differentiation. Most of what we differentiate is what we call explicit differentiation, although we don't call it that, we just call it differentiation. But explicit is when we explicitly make one of the pronumerals the subject of the formula. Implicit differentiation is when we don't bother with that. So more complicated functions, again, let's go back to this x cubed plus y cubed equals 1. So rather than making y the subject, I could differentiate that implicitly. So I want to draw x cubed plus y cubed equals 1. So what do I notice? Well, as I mentioned before, it's got symmetry in the line y equals x. Swap the x and the y's around, you get the same function. So here's my graph. Whoop. I'll just draw in the axis of symmetry there, y equals x. I know it passes through 1, 0 and 0, 1. Basically the two intercepts, very easy to find. Substitute x equals 0, substitute y equals 0. And of course if it goes through 0, 1, because of the symmetry I know it's going to go through 1, 0 anyway. But that just confirms it. It's asymptotic to the line y equals negative x. Now you might not have noticed that straight by looking at it. But think about it this way. Y cubed, if I did rearrange that, I'd get equals 1 minus x cubed. Well, if it's always 1 more than minus x cubed, it can never equal negative x cubed. And if y cubed can't equal negative x cubed, then y can't equal negative x. So y equals negative x turns out to be an asymptote. So I'll draw that in. Whoop. Differentiate implicitly. 3x squared plus 3y squared divided dx equals 0. There's my derivative, minus x squared on y squared. It's always negative, because x squared on y squared is going to be positive, but it's negative that. So it's always decreasing. I know the curve is just going down. Except at the point 1, 0. If I sub in 1, 0, my derivative is undefined. So I know it's got a vertical tangent at that point. And at 0, 1, I'll have a horizontal point of inflection. And again, that makes sense because of the symmetry. If at 0, 1 it had a horizontal point of inflection, you reflect it in y equals positive x, and you'll have a vertical tangent. What does it look like? Whoop. Something like that. Something like that. In fact, all of the odd ones, so x to the power of 5 plus y to the power of 5 equals 1, will have that sort of shape, except for power of 1. 1 is, of course, odd. And x plus y equals 1 would be that asymptote. Not that asymptote. So it'd be parallel to that asymptote, but it'd go through 1, 1. This is a straight line. So what happens, it's actually very interesting if you were to look at it. The curve, as you change the powers, odd ones, starts with the straight line going through 1, 1. Then change it to an even power, we get a circle that goes through 1, 1. Sorry, when I say 1, 1, I don't mean the point 1, 1. I mean 1 on the y-axis, 1 on the x-axis. X cubed, you now start getting this one. If I was to do x to the power of 4 plus y to the power of 4, again, you've got a rounder object. And so it keeps alternating from this sort of shape to a shape that's enclosed. As that power approaches infinity, what do you get? And I'll give you a hint. If we think of infinity as an even number, a square. So there is your equation for a square. The limit as k approaches infinity of x to the power of, well, we'll say 2k to ensure it's even, plus y to the power of 2k is equal to, a constant, 1. You will get a square. And if you don't believe me, we can have a look at Desmos later and actually graph that, and you'll see, yes indeed, it graphs